We're going to start with a review over IR, HNMR, CNMR, mass spec, and go over some of the more common reactions for the first half of this session. And then for the rest of the session, we're going to go ahead and do some practice problems that we put together. And you guys can ask questions anytime throughout the session as well. So first, we'll go ahead and start off with IR.
Hi everyone, my name is Safa and I'm going to start the discussion about IR. So the first thing to talk about is what electronic EMR rays can tell us about molecules. With IR, we're specifically looking at infrared light, and when it hits a molecule, different bonds in the molecule give us different responses, and we can plot that response on a graph with the frequency on the x-axis and the transmission on the y-axis. And once we have that, we can start to look for patterns in it. Next, we can talk about some uses of the IR spectra. IR is most useful for providing information about what kind of bonds you have or what kind of functional groups you have. IR can't really tell us the exact structure or formula, how long the carbon chain is, for example. So it's usually used in combination with CNMR or HNMR to get a more detailed look at the structure. There are a few ways to approach IR. The first thing we usually do is start at 3000. That's where your carbon-carbon bonds will be. So saturated molecules, for example, a straight carbon chain will have its peaks just below 3000. If there's any unsaturation in the molecule, for example, double bonds, triple bonds, those will have their peak a little bit above 3000, and then they might also have companion peaks later on in the spectrum, which we will show in a little bit. Another big area is 1700. This usually has a very identifiable carbonyl peak if there is one in the molecule. You can use the presence or absence of other features to tell what kind of functional groups you may have. For example, aldehydes have twin peaks at 2700 and 2800. Those are sometimes called fangs. Carboxylic acids will have a super broad peak that you can see. You can tell a ketone by the lack of these additional features. And then the last thing to look at is that the region below 1000 is called the fingerprint region, and we usually disregard it because it's difficult to interpret. So that's not something that you should have to stress about on your exam. We'll look at a graph of alkanes versus alkenes. Here you can kind of see the peak below 3000 for the one on the left. That's typical of a fully saturated molecule, whereas the one on the right has a double bond in it, and so you have a little bit that goes above 3000. It's at 3080 over here. Alkane. Okay, alkynes and nitriles have.
Sorry.
No, you're good. You're good.
Okay.
Alkynes, so triple bonds, have a sharp peak at 2000. That sharp peak is based on polarity, so it will actually differ based on where that triple bond is. If your triple bond is a terminal triple bond at the end of the molecule, your peak will be a little bit stronger. If it's right in the middle, you might not even see it. It's generally a weak to medium band. If you have a nitrile, which is a carbon triple bond with nitrogen, that will show up in about the same place, but that tends to be a lot stronger because nitrogen is more polar. And again, looking at that 3000 region, you see a little bit above 3000 because the molecule is not fully saturated. Alcohols and carboxylic acids are the most prominent functional group on the IR. It's usually the one that you can identify the fastest. They're very strong and they're very broad. The difference between the two is that carboxylic acids are a lot broader. They go from above 3000 all the way below 3000, while alcohols usually stay very clearly above 3000, as you can see on the left here. Another big difference is that Alcohols are not carbonyls, and so they won't have a matching peak at 1700, whereas carboxylic acids will have that peak at 1700. Speaking of carbonyls, we have aldehydes and ketones. Both of those have that peak at around 1700. They're very prominent. The difference between the two, as we mentioned a little bit earlier, is that aldehydes have two like FANG kind of peaks at around 2700, 2800, whereas ketones won't have that at all. So you can usually detect ketones by the lack of any other matching peak or FANG or broad thing like in carboxylic acid. The last main functional group that we can tell from IR are amines. Amines are usually above 3000, and we see little spikes based on the degree of the amine. So primary amines are NH2. They have two nitrogen-hydrogen bonds, so they'll have two spikes. They look like two teeth usually. Secondary amines will only have one bond, so there's only one spike. And then with tertiary amines, you don't have any bonds, so it doesn't really show on the IR spectrum. You would usually look at the formula of the molecule then to determine whether there is an amine. We've also provided a table with a summary of stretching frequencies. This can be very useful to study to get an idea of what you should expect to see in each region. We mentioned above 3000 alcohols, amines, alkynes. A little bit above 3000 are alkenes. You have your alcohol a little bit above 3000 as well, and then your alkane is right below 3000. That's your fully saturated carbon. Your triple bond should have that matching peak at 2200. Again, it's a little bit stronger for nitriles because of the polarity of the nitrogen. And then 1700 is a big region for carbonyls. We're not looking too much at things that are a lot below 1700, and especially below 1000. Does anyone have any questions on IR functional groups? Okay, sounds good. And remember, if you have any questions, feel free to leave them in the not that I'm aware of. Unless your professor has specified that you will have a table of values, I would assume that you wouldn't.
I think if I remember correctly, I think Zero, so one of the OChem team leads was telling us that they probably will give you an IR chart, but he wasn't very specific about whether they're giving an H&MR chart just yet. So that's something you can ask in class tomorrow. That's always just better to ask, just to be safe. But I think for sure all professors for non-Novak students have decided to give an IR chart. All right, so if nobody has any questions about IR, we're going to go ahead and move on to HNMR, CNMR, and mass spec. So one of the most important things that you're going to see in an HNMR spectrum is a chemical shift, and that depends on the environment of the proton around it. So a proton shift is going to be due to the nearness to electronegative atoms. So some of the electronegative atoms that you're looking for are oxygen, nitrogen, or halogens, and some unsaturated groups such as a C double bond, and then a carbonyl group, as well as aromatic compounds. So there is downfield and upfield on an HNMR spectrum. So downfield is more deshielded, and it's going to show to the left of the spectrum. So what it means by deshielding is that the electron negative groups are going to pull the electron field from around the nucleus of the proton towards the more electronegative atom. So the proton is going to be less shielded by that electron shield, so it's going to be more to the left. And then the upfield is opposite. It's going to be more shielded. You're not near an electron withdrawing group, so the electron shield is going to remain closer to the nucleus of the proton. So this is just the top picture here shows some of the common groups that you'll see in certain ranges of an H&MR spectrum. So you're going to usually have sp3 carbons towards the upper right side of it. And then you're going to see carboxylic acids and aldehydes all the way downfield to 10. You'll see about an aldehyde, and then 10 plus is where the carboxylic acid will show up. And then another important thing is that an aromatic ring shows up at around 7 to 8. And then the bottom one here is just a CNMR spectrum, but we will get to that in a little bit. So another important thing that shows up on an IR spectrum is splitting. So non-equivalent protons are going to split the signals of other protons because those neighboring protons are going to disrupt the magnetic field. So for simplicity, you can determine if a signal is going to be split by a specific hydrogen if they're no more than 3 bonds apart. And then additionally, alcohols and amines are not going to split due to a rapid proton exchange. And in order to find the splitting pattern, you're going to use the n+1 rule, where n is the number of neighboring protons. So if we look at this example molecule over here, so hydrogen A's have 2 neighboring hydrogens, which are going to be the hydrogen B's. So in order to find that split, you're going to do 2 plus 1, and you'll get 3, which is a triplet. And on a spectrum, you would see 3H comma T. And then for hydrogen B's, you're actually going to get a slightly different splitting pattern because it's neighbored by 3 hydrogens to its left and then 2 hydrogens to its right. And since HA and HC are chemically different, they're going to cause a slightly different split. So if you do the splitting pattern for HA, you'll get 3 plus 1, which is a quartet. And then for HC, you would get 2 plus 1, which is a triplet. So on your spectrum, you would see something like 2H comma T of Q. And then if you look at HC, it's only neighbored by 2 hydrogens, which is HB, because the molecule to the right, the atom to the right is an oxygen, and it has no hydrogens on it. And then lastly, for D, the carbon double bond with the O here is not going to have a hydrogen. So it would be neighbored by 0 hydrogens. So you would end up with a singlet on the spectrum. So these are some of the common H&MR patterns that might show up. So if you see a singlet of 9 hydrogens, it means you have a tert-butyl group. And then if you see a 6 hydrogen and then a 6 hydrogen doublet and a 1 hydrogen septet, it's going to be an isopropyl group because you have 2 methyl groups that are chemically identical. So that would be the 6 hydrogens. And then that carbon that they're attached to will have 1 hydrogen attached to it. And then lastly, an ethyl group is going to show up as 3 H's and 2H, and you would get a triplet and then a quartet for those. So in summary, the H&MR spectrum is going to tell you the number of chemically different hydrogens, as well as the environment of the specific protons, whether they're shielded or deshielded. The splitting is going to be determined by the n+1 rule, and then it'll show the number of hydrogens, which is the integration or intensity. So some of the tips on how to approach an H&MR problem, I wouldn't just start drawing when you see an H&MR spectrum. I would start labeling. So the first thing you would do is that they're going to give you the empirical formula of the molecule. So you would find the degrees of unsaturation using this formula. And then if you have 4 or more, it usually means you're going to have at least 1 benzene ring in there as well. And then you're going to identify the functional groups based on the chemical shifts from the chart. And then you're going to determine the number of neighboring hydrogens based on the splitting pattern. So you're kind of going to go backwards. So if you see a triplet, you're going to do 3 minus 1, and that would give you 2. So that means that those 3 hydrogens are going to have 2 neighboring hydrogens. And then if you see 2 hydrogens, comma T of Q, that means you know that these two specific hydrogens are going to be in between two chemically different hydrogens. So one of them is they're going to be split by two neighboring hydrogens. It'll be two on one side and then three on the other side. And then next, you're going to draw the structure based on all the information you have determined. And then lastly, just to make sure your structure is correct, make sure it matches the HNMR spectrum before you move on, just so that way you can check your work. And then now moving on to carbon HNMR, or carbon NMR, sorry. It's going to identify the number of chemically different carbons that are available in the molecule. It's not going to tell you the number of carbons that are there because you can always have symmetry. And like HNMR, the chemical shifts are going to depend on the chemical group that the carbon is attached to. Once again, the electron negative groups will pull electrons away from the nucleus of the carbon, which is going to leave it more exposed to the external magnetic field, which is why it shifts to the left of the spectrum. And then, like I mentioned, for example, if you have a molecule that has 6 carbons, but there's only 2 peaks on the NMR, then that means the molecule is going to be symmetrical. So this is just an example for how to identify the chemically different carbons. So the first thing I would do is figure out a plane of symmetry. So this plane of symmetry, as you can see, there's a blue dot and a green dot. The plane of symmetry is going to go through those lines. So the blue is chemically different than the two that it's attached to, but those 2 pink ones are going to be chemically the same because they're both attached to that purple carbon as well as that orange carbon. So on an exam or something, one thing you can always do to help you keep track of the number, to keep track of the chemically same carbons, is you could just draw different shapes on them and then count how many like different shapes you have, and then that can help you keep track of which carbons are equivalent and which ones are not. So in summary, the CNMR spectrum is going to tell you the number of chemically different carbons, the environment of those carbons, but it will not tell you the number of carbons the molecule has. And then lastly, we have mass spec. So it's useful for measuring the mass to charge ratio, and the peaks are going to be the M to Z ratios plotted against their intensities. So the sample is going to be ionized, usually to cations, by the loss of an electron. And the compound gets split into a cation and a radical, and only the cation is going to reach the detector. So remember, the masses on a mass spec are going to correspond to the mass of the cation. And since you also get a radical, the intensity of the peaks on a mass spec are going to be dependent on the stability of the complement radical. And then usually you'll have an M plus peak, which is going to be the mass of the chemical usually. And then to calculate fragment weights, like if you were to calculate the fragment weight of a methyl, you would have the atomic number of or the mass of a carbon, which is 12, plus 3 hydrogens, which would give you 15. And then similarly, an ethyl group is going to be 14, and then so on. So now Safa is going to take us, or does anybody have any questions over CNMR, HNMR, or mass spec so far? Oh, I can't see the chat if people are asking questions in there.
One question is, how is deshielding ranked?
Oh, how deshielding is ranked. So it's going to depend on the electronegativity. So for example, if you had an oxygen or a nitrogen, nitrogen is more electronegative. Hold on. Sorry, oxygen is more electronegative than nitrogen. So the oxygen would be slightly more, if you had a proton attached to a carbon that's like, or if you had a proton that's closer to an oxygen compared to a nitrogen, that would be slightly more downfield compared to the one that's near the nitrogen.
I don't see any other questions, so I can go ahead and get started with OChem 1. If anyone has any questions on material we've already covered, feel free to leave it in the chat and we can get to that. We're going to start with a review of some OChem 1 reactions that are relevant to this exam. The first is reduction of carbonyl compounds. So this is the opposite of the oxidation that you're learning. We have two main reducing agents. We have LAH and we have NABH4. NABH4 will only work on aldehydes and ketones, whereas LAH can work on all of them: aldehydes, ketones, esters, carboxylic acids. And what'll basically happen is you'll remove the double bond and you'll have just an alcohol in place of a carbonyl. So you can kind of see with this ketone how it became a secondary alcohol, and then the aldehyde became a primary alcohol. And the aldehyde is the easiest to reduce, and then the carboxylic acid is the hardest to reduce, which is why NABH can only work on the ones that are really easy to reduce. Another reaction from OChem 1 was the Grignard reaction. In the carbonyl compound that
Oh, is there a slide for that, or?
that is the slide. Nucleophilic attack is the.
Oh, sorry.
You're good. So in the carbonyl compound, that carbon at the carbonyl carbon basically that's right under that double bond, that one is very electronegative. So when you use MgBr, which is your Grignard reagent, it will attack that electrophilic carbon, and you will create an alcohol. That's another way to create an alcohol from a carbonyl, and it can also add carbons as well. We also had some alkene chemistry from the end of OChem 1. There are a few ways to make carbonyls. The first is to use warm or acidic or concentrated KMNO4. And that will basically cleave into a ketone if it's fully substituted, or a carboxylic acid if it wasn't fully substituted. You can do the same thing with ozone or O3. And then if you don't want it to go all the way to a carboxylic acid, if you want a ketone with an aldehyde, you can use O3, but with zinc or with CH3 and sulfur. You can also get alcohols from an alkene, so either using mercury with water, NaBH4, or using BH3THF with peroxide. Those are a few ways to create alcohols. And the difference between the different reactions is just whether it goes in the most substituted place or not, the Markovnikov or anti-Markovnikov position. You can also create diols, which is two alcohols in place of the carbons where that double bond was. So that would be using OSO4 with a peroxide, or if you use cold dilute KMNO4 with NaOH. So just be careful when you see KMNO4. If it's warm or acidic, you will have carbonyls, but if it's cold dilute, you will have two alcohols. Now that we have that foundation, we're going to take a look at some reactions that you've learned this semester. The first thing that you probably started with is the oxidation of alcohols. So this is the reverse of the reduction that you learned last semester. With primary alcohols, they can be oxidized all the way to carboxylic acids using some like major oxidizing agents. Think of that as the opposite of LAH. So with Kr chromium O3, with NaOCl, with K2 chromium O7, those ones will take your alcohol directly, primary alcohol directly to a carboxylic acid. We also have some weaker oxidizing agents such as PCC, DMP, or SWERN, and those will stop at an aldehyde. A good way to remember it is that the ones that will stop at an aldehyde are either abbreviated or they're named after a person. So PCC, DMP, or SWERN. Secondary alcohols will always be oxidized to ketones regardless of what you use. So whether it's one of the big oxidizing agents or little oxidizing agents, it will be the same thing. And then tertiary alcohols are never oxidized. This is because if you take a look at the secondary alcohol and the ketone, you are taking away a hydrogen from both the alcohol and that carbon and creating a double bond in a similar way to the E2 mechanism. When you have a tertiary alcohol, there is no hydrogen left on that central carbon, so it's not possible to make a double bond without, having 5 bonds to carbon, which we know isn't possible. Oh, this is the same thing.
Oh,
Another thing that you learned this semester is converting alcohols to alkyl halides. So there are 2 different ways to do that. The first one is just for alkyl chlorides. So that's using thionyl chloride or SOCl2. That will convert primary alcohols using the SN2 pathway, and then it can also convert secondary and tertiary alcohols using the SN1 pathway. So your alcohol will attack the thionyl chloride and kick off that oxygen, and then HCl will leave and then re-attack the molecule, and you'll end up with that Cl displacing the oxygen or that alcohol group. The second way that you can do this is using a phosphorus halide, so PCl3, PBr3, or P with I2. This can make all types of alkyl halides, but it can only do primary and secondary alcohols. And so this one uses the SN2 pathway as well. Your nucleophilic alcohol will attack your phosphorus halide, and you will kick off your leaving group, which is that PCl3, and you will be left with just your chlorine in place of the alcohol. If you want a tertiary alkyl bromide or iodide, then for that we use something separate, which is HBr or HI. This is a good chart to kind of summarize. SOCl2 will give you any kind of chloride, primary, secondary, tertiary. And then phosphorus, PBr3, PI2, those ones will give you your bromide, iodide, but only primary and secondary. So you will look at HBr or HI for tertiary bromides or iodides. Another major reaction is the ester formation. So one way of doing this is to combine carboxylic acids and alcohols. This is usually a reversible reaction between a carboxylic acid and an alcohol to form an ester. To push the reaction in the direction of ester formation, we use Le Chatelier's principle, which is basically you remove something from one side to push the reaction in the other direction. So in our case, we're removing water, and that removal of water is called the Dean-Stark distillation. So that process, you basically see the the carboxylic acid OH and the alcohol OH. So from those two, 2 hydrogens and 1 oxygen will leave as water, and then you're left with just that ester oxygen. Another very efficient way to do this is instead of a carboxylic acid, you use an acid chloride. So instead of H2O leaving, you'll have HCl leaving, and you'll still be left with that 1 oxygen from the alcohol as your ester oxygen. We usually use triethylamine with this reaction to capture the released HCl gas. We can also make ethers using Alcohols, so we start with a deprotonated alcohol or an alkoxide nucleophile, and then it will attack any primary electrophile, and you can create an ether using SN2 chemistry. One modification that you can make with alcohols is using tosyl chlorides. As we remember from Oh, okay. There's a quick question, which is what is the difference between Dean-Stark and Fischer esterification? That's a really good question. Fischer esterification is the entire reaction, which is combining a carboxylic acid and an alcohol to create an ester. The Dean-Stark distillation is just the process of removing water. So a Dean-Stark distillation doesn't have to be part of a Fischer reaction. It can be part of other reactions as well. Any reaction where you're removing water in that distillation process is a Dean-Stark distillation. So that's a technique that we use in order to conduct the Fischer esterification, if that makes sense. With alcohols, we know from OCHEM 1 that alcohols are not, or OH is not a very good leaving group. We used to protonate it to have water as a leaving group. One thing that we can do in OCHEM 2 is change the alcohol for something called a tosyl chloride. So it will react in that same SN2 mechanism that we discussed with esters. So you have your chloride and your alcohol, and then you're left with an ester. This new leaving group is called a tosylate, and it is easily removed, so then it will react with any nucleophile to create further reactions. So you can react this with a bromine, you can react it with just more carbons if you wanted to add it, you can create amines. There are a long list of reactions that you can do when you can conduct SN2 chemistry with tosylates. One thing that tosylate esters can also do is be reduced by LAH to form a hydrocarbon. So if you have an alcohol on a molecule, it's not possible to just remove that alcohol unless you're creating a double bond. But if you convert it to a tosylate ester, you can then reduce it and have that tosylate ester leave. I wanted to quickly go back to Grignard reagents and talk about how we can apply them this semester. So one thing that you might have to do in synthesis is to create a Grignard reagent yourself, and that can be done by starting with an alcohol and creating an alkyl chloride. So like we talked about, you can use SOCl2, for example, and you've changed your alcohol to an alkyl chloride, and then you can just react with Mg, and you have your MgCl. You can do this with Br, you can do this with Br, you can do this with Br. So you can have a MgCl or MgBr. Once you have your Grignard reagent, it's a really good way to make an alcohol. It's an alternate way to just a reduction because it can be used to add carbons. So for example, we see an aldehyde here, and when it's attacked with a Grignard reagent, you get a secondary alcohol with that extra carbon change. And once you have that, you can then react with a tosyl chloride to create a good leaving group that can be reduced. This is an example of a kind of step-by-step mechanism or synthesis that you might be asked to do. And hopefully you can see the difference between using a reducing agent directly and using a Grignard reagent. So with this aldehyde, if you had used LAH or NABH, you would have been left with a primary alcohol. But since you used Grignard reagent, you now have a secondary alcohol with 2 extra carbons added to it. So just be mindful of what your question is asking or what they're looking for, and decide which one is more appropriate to use. Does anyone have any questions on the OCHEM 1, OCHEM 2 chemistry or the reactions? Okay, if not, I think we're going to start going into breakout rooms to work on some problems. Give us a moment while we get that settled. Yes, just give me a moment. Okay, hi everyone. We have some practice problems for us to apply the things that we just talked about. Before I begin, I just want to ask if anyone has any questions that we talked about that you weren't able to ask before the breakout rooms begin, or anything that you would like additional clarification on. Yes, of course. I'm going to try and draw this over here 1 second. Are you able to see an alcohol at the top of this page? Okay, perfect. So actually, hold on, this might be better drawn like this. Okay, this is a secondary alcohol, and it will, if it reacts with a tolsyl chloride, we can have OTS. That alcohol is not a good leaving group, so we couldn't remove it on its own. But OTS, when reacted with LAH, you will basically do an SN2 reaction and you'll put a hydrogen instead of the OTS. So this H will kind of go here and this will leave. Does that make sense? Yeah, no problem. Okay, so the first question asks us to rank these molecules by their downfield shift. So whatever hydrogen in here will have the furthest downfield shift in a molecule. And downfield shift is based on electronegativity and orbitals. So if you have nitrogens, if you have oxygens, that tends to shift molecules downfield. If you have double bonds, that does too. Based on that knowledge, what do you feel might be the most downshielded molecule? Okay, aldehyde is definitely downshielded. Um, so we'll say maybe it's around 10. What would be the least downshielded molecule? Downshield is to the left. Cyclohexane. So I'm going to put this one as 5. Okay, what might be the next least downshielded? Yes, that's right. And why is the cyclohexene a little more downshielded? Okay, perfect. So then what are we thinking is our third most downshielded? Or like our middle one? Benzene ring? Okay, everyone agrees? Okay, that's right. So we see how that addition of those double bonds continues to deshield our molecules. The ones we have left are both benzene rings. One has an aldehyde and one has a carboxylic acid. Based on electronegativity, which one do you feel is most downshielded? Carboxylic acid, yes. because that one has 2 oxygens, whereas the aldehyde only has 2. This is a little bit above 10, 10 plus maybe. This one's probably around 6. This is around 1, around 2. So that is perfect. Okay, let's look at part B. Okay, so this one we're ranking by splitting in a molecule. So for each one, it might have multiple signals. We're looking at the one that has the greatest splitting. So for part B, which hydrogen do you think would have the most splitting? Or sorry, for part B, the first molecule, the one that we see on the very left, the ester with an ethyl and an isopropyl. Um, let me take this carbon right here. What do you think its splitting is? Yes, yes, more neighbors. So first we can talk about the hydrogens that are next to it, and then we can look at the splitting. So for this carbon in blue that I've circled, how many neighboring hydrogens does it have? Okay, yes, this one has 3. So I'm going to put 3 and then I'm going to put quartet. Okay, we have this other one here. How many hydrogens does it have next to it? 6, perfect. So we call that a septet. Okay, so the most we've got out of this one is 6. What about the second molecule? Do you see a place that might have a lot of neighboring hydrogens? Yes, exactly. This one is next to 3 hydrogens on the left side and 2 hydrogens on the right side. So these 3 hydrogens become a quartet, and those 2 hydrogens become a triplet. So when we're counting splitting, we multiply that together. So a quartet of triplet would be 12 peaks. 12 peaks. And then with the first molecule that we did, that septet would be 7 peaks. Does everyone see how you would count the splitting? Whether it has neighboring hydrogens on just one side or both sides. Let's take a look at the third molecule. Is there any? Okay, no worries. Do you understand the one that's in blue? Okay, so that 12 is from having a quartet on the left and a triplet on the right. So we kind of multiply quartet by triplet. So we think of it as 4 times 3. Okay, we added all the neighboring hydrogens on each side and then added 1. Um, we do add the neighboring hydrogens, but when we have hydrogens on both sides, so for example, for the one in blue, we've just listed septet. But for the one in green, if we were to just add all of the neighboring hydrogens, we would say, okay, we have 3 hydrogens on the left and we have 2 hydrogens on the right. So that's 5. And we would add 1 and say, okay, 6. That's a sextet. But we don't do splitting that way. We will refer to it as a quartet of triplet. And that's to clarify that we have a quartet on one side and a triplet on the other. Yes, you're just looking for the carbon with the most neighbors. That will give you the greatest splitting. Yes, yes, exactly. But I just wanted to clarify because you might see on your test something that says triplet of doublet, for example. And that's to tell you you have a triplet on one side and a doublet on the other. If you were to just count up all the neighboring hydrogens and add 1, that would be a pentet, but you wouldn't know how those 5 hydrogens were distributed. Does that make sense? That n+1 rule still applies, but we use it if you only have one side with neighboring hydrogens, like for that molecule in blue. And as we continue with these molecules, hopefully it will become a little more clear. For this third molecule, does anyone see a carbon with neighboring hydrogens? Okay, yes, so there's definitely this 2 hydrogen, and it's next to, this is a quartet, so this will have 4 peaks. This one over here is a doublet, sorry, no, triplet, because it's next to 2 plus 1, so we will see 3 peaks. And the reason why this one at the end is a triplet is because the carbon next to it has 2 neighboring hydrogens. So then n+1 or 2 plus 1 would be 3. Does everyone see how counting that the splitting works? Yes, that is a CH3, but we're counting the neighboring hydrogens. So for that CH3, it would be 3 hydrogens triplet. And that triplet would give us 3 peaks. That triplet comes from that CH2. And then for the CH2, that's a 2 hydrogen quartet. So it itself is 2 hydrogens, but it's next to 3 hydrogens. So those 3 hydrogens that it's next to is what gives you your quartet. Does that make sense? Oh, okay. So there are only 3 hydrogens. The 4 comes from the n+1 formula. So if you have 3 neighboring hydrogens, you're going to go 3 plus 1 is 4, and so you have a quartet. Yeah. And I think we're going to see that in, actually, no, we might not see that in this question, but we'll come back to that for sure. For this fourth molecule, do we have any carbons with neighboring hydrogens? No. So this carbon, what kind of peak would it have? What do we call it? Singlet. Okay, perfect. And then this as well. So that's 1 peak and 1 peak. Oh, I wanted to switch colors. Okay, so for this last one, do you see any carbons with neighboring hydrogens? Okay, can you label them for me? Or if you see one that has the most splitting, you can just label that one too if you don't want to do them all. Okay, yeah, so we have 6H doublet, so that's 2 peaks for this carbon. What about this one at the bottom? Actually, let's not do the center one. Let's do the one on the right-hand side. So this right one is next to how many hydrogens? It's next to 1. So that would be 2 hydrogen doublet again, 2 peaks. And then this one in the middle. Okay, so this is kind of where that like x of x thing comes in. So on the right-hand side, how many neighboring hydrogens does it have? 2. So that's a triplet. And on the left-hand side, how many does it have? 'Yes. So because there are 2 symmetrical methyl groups or identical methyl groups with 3, we count it as 6. So that is a triplet of septet. Um, so that one is going to have 21 peaks. So based on this information, so for each molecule, molecule 1 has maximum 7 splitting, molecule 2 has 12, 3 has 4, 5 has 1, and then, sorry, the counting was not right. But based on this, do you guys have your ranking for which one has the greatest splitting and which one has the least splitting? So you're not counting every single splitting within the molecule, but just the signal with the most splitting, if that makes sense. So in your third molecule, you have a triplet and a quartet. You would just compare the quartet. Oops. Let me try and find a different color so that we don't get mixed up with the peaks. Okay, um, so the least splitting is 1. Okay, 1, 2, 3, 4, 5. Um, does everyone agree with that ranking? With 1 having the least splitting and 5 having the most? No, you don't agree with it? What do you not agree about? Okay, third and fourth. Based off of the DCABE that Tochi put in the chat. So Fiona, you're saying switch 1 and 2, and Brandon, you're saying switch 3 and 4. So why do you both say that? Let me quickly do that. Fiona, does this look better to you? Okay. Yes. Um, The idea was really good the first time, but there were a few small corrections to make. Thank you so much, everyone. So for, oh, okay. I'm glad. No worries. I'm glad that you guys are participating and answering. And it's definitely easy to mix up small things. Or I might have not interpreted the chat correctly. But yes, so 1 and 2 are switched because 1 has only a singlet, whereas 2 has a quartet. And then 3 and 4 are switched because 7 is less splitting than 12. Um, does anyone have any questions on 1A and 1B? If not, we're going to take a look at 1C. So, oh yeah, go for it. 4, 3, 2, and 5. 4, 3, 2, and 5. Sorry. Okay. I think you are right about that. I'm going to come back to this question really quickly because I want to make sure that I've explained that splitting right. And I'm going to double check if that n+1 rule applies when we're counting this. So this could be 3, 4. Hold on. I see what you're saying, and we can come back to that for sure because I want to make sure that we clear up that confusion. In the meantime, let's quickly cover CNMR. How would you guys, what is the factor that we're looking at when we're trying to see how many signals a molecule has in CNMR? Symmetry. Okay, perfect. So everything that we have here has 6 carbons, but they won't all have 6 signals. So for the first molecule, how many signals do you think we'll have? 1 signal? Okay, perfect. And that's because every single carbon here is identical. For the second molecule, how many signals do you think we'll have? 4 signals. Okay. So let me try and color that for you. Can you guys see the different colors okay? Okay, perfect. Is this what you were thinking? Yeah, that's perfect. Good job, everyone. Third molecule, how many signals? 3 signals. Okay, perfect. Okay, fourth molecule, how many signals? 2 signals. Okay, and then fifth molecule, how many signals? 6 signals. Yeah, every single carbon in that one is different. So, can someone type our final ranking into the chat, please? Actually, it looks pretty similar to the number of signals, basically. Okay, that is perfect. So let's see. Between I want to see which one to start with between HNMR, CNMR, figuring out a molecule from that, and doing alcohol reactions. Which one do you feel, which one would you prefer to start practicing with? Or which one would you want to spend more time on? Reactions? Okay. Let's start with that before we come back to HNMR and IR then. Okay, so we have some reactions here. For A, we have an alcohol and we have tosyl chloride and NaCN. Um, what worksheet is this? This is a list of problems that we have put together that relate to your exam. We will send you the problems. We should send you the problems with the key after the session so that you're able to work this out. But this kind of draws on questions from different professors or previous exams. Yeah, no worries. For A, an alcohol with tosyl chloride and NaCN, what do you think is the result of that alcohol with tosyl chloride? OTS, great leaving group. Okay, perfect. So let me try and draw this. OTS. Okay, and then when OTS reacts with NaCN, um, that's a good question. Let me check that for you really quickly. Um, while I do, does anyone have, I know that OTS with NaCN is definitely SN2. Let me double check the other one. Just give me one moment. I know it displaces the hydrogen on the H, but I'm not sure if it's an SN2 reaction. And I don't think that it is because our stereochemistry doesn't invert in that step. But I'm definitely going to make a note of this and double check before you leave. Appreciate. Okay. So, yeah, no problem. So with tosyl chloride and NaCN, what will happen? Okay, perfect. So this becomes Cn minus. And where will that Cn minus go? Yeah, that's perfect. So this part is SN2 for sure. I will double check about this one. Okay. Let's okay. I think B and C are not super common. Let's take a look. Okay, let's do D really quickly. Does anyone know what the outcome of D would be? Alkyl chloride. Okay, perfect. And is this SN2 or SN1 chemistry? So thionyl chloride, it'll actually do primary alcohols using SN2, and then it'll do secondary and tertiary using SN1. So when I draw this this chlorine group on this carbon, should I invert the stereochemistry or no? No, perfect. Yeah. Just a small thing to keep in mind with thionyl chlorides. If you're doing phosphorus halides, then it's all SN2. Um, let's see. Do you have an idea of what NaH will do to the alcohol for E? Yes, alkoxide, that's perfect. So you have a benzene ring, that's another way to draw it. Sorry, my bad, I'll try and. Okay. And so now what will this do with that alkyl bromide? Yes, that's perfect. It will attack Br and it will create an ether. Good job, everyone. So we will have something that looks like this. Let's look at F. What does PCC do? And by the way, this CH2Cl2 is not a reaction. This is just the solvent that it's in. So you don't have to worry about that. If it's a reaction, it should be numbered like an E where it has like number 1, then number 2. Since it's not something that you have to worry about. Yeah, that's perfect. And if I wanted to make this a carboxylic acid, what could I use? Perfect. Okay, we have one more reaction problem, I think. Yeah, that's it. And then we can go back to our CNMR, HNMR, IR. So on this page, the last question. So this is a series of reactions. And at the end of the reaction, they're saying that the product you should get should be an aldehyde. You need to check if that's correct. And if it's not correct, what you would do differently. So we can go through this step by step. So when you have the alcohol and the phosphorus bromide, what happens in that one? OH to Br. Okay, perfect, Fiona. Okay, and then when we react with Mg, what do we make? Grignard? Okay. And when that Grignard reacts with a formaldehyde, what do we get? Question 6, sorry, at the bottom of the page. The rest of the page is CNMR, HNMR questions, which we can definitely get to in just a moment. Okay, so when a Grignard reacts with a formaldehyde, what would we get? Alcohol? Okay, perfect. What kind of alcohol? Not carboxylic. Usually it's whenever you react a Grignard with a carbonyl, you end up with an alcohol, but the different kinds of carbonyls will give you different kinds of alcohols. Yes, primary alcohol. Um, if you had an aldehyde, it would give you a secondary alcohol. If you had a ketone, it should be a tertiary alcohol. Um, so this formaldehyde will give you a primary alcohol. Okay, perfect. Um, and then when we react a primary alcohol with a strong oxidizing agent, what do we get? Yes, Brandon, that's perfect. Okay, we get a carboxylic acid. And since that's not what we originally expected, what can we change in this to give us our aldehyde? Yeah, that's perfect. PCC. What's another thing that we can use? DMP, Swern. Yep, that's perfect. And you will only need to list one on your exam, but I just want um, to make sure that you're comfortable with all of them. Um, okay, perfect. Um, let's do IR really quickly. So here we have 4 IR spectra and 10 compounds listed. So, sorry. Um, I would like you guys to match the IR compounds that you see with some of the um, molecules that you're shown. We don't have 10 IR spectra, so you're not going to use all of them. But let me know what identifiable functional groups you see in your IR spectra, and hopefully that will help. So for the first one at the top, do we see any? Okay, first one has carbonyl. And where do you see that carbonyl? 1700-ish. Okay, so we're saying this is the carbonyl. Possible. Do we see anything else in this IR spectra? And the numbers are a little bit difficult to tell. I apologize for that, just because it's kind of zoomed out, so it's difficult to tell exactly like 2700, 2800, etc. But hopefully when we put everything together, we can use process of elimination since this is kind of multiple choice. We do have an amine here. What kind of amine do we have? Yes, primary amine, that's perfect. Okay, so based on this information, is there anything that we see that could match what we have? B? Okay. Yeah, B definitely has the primary amine, and it's the only one that does. Um, Whoever said carbonyl for the functional group, that is a really good observation because it's in that area. Unfortunately, this one didn't have a carbonyl because this peak is actually closer to 1600 than 1700. If you look between 2000 and 1500, 1700 should have been right in the middle, and it's a lot closer to 1500. But that's not really your fault because this is a little bit difficult to read. Yes, that is the aromatic 1600 peak. So something to keep in mind because they're close, but they definitely shouldn't give you a question like this without having a formula or examples of the molecules. So it's not a guess that you should have to make. For the second question, um, the package should be sent to you. Um, After the session is over. As far as I know, I don't. Yes. So the most updated information that I've heard is that IR should be given for all professors. HNMR, CNMR, I'm not sure about, especially because HNMR and CNMR can vary. Those ranges aren't exact, especially if it's like, okay, a carbonyl is at 2, but let's say it's a carbonyl, but it's next to a nitrogen. Then that would move it up a little bit because you have two things happening at the same time, and that chart doesn't really account for that very well. So to the best of my knowledge, your professors will not give you one. I would definitely double check with them. The good thing with HNMR, CNMR is that there's not as many things to look out for, and you can usually use the formula to help a little bit with what that molecule should look like. There are a few big ones. Aldehydes are at 10, carboxylic acids are at 12, ester oxygens are at 4, carbonyl carbons are at 2. Those four I feel like come the most often. So if you know those, that takes a big stress off your shoulders. Let's look at the second IR spectra really quickly. Is there anything identifiable here? Yes, yes, those are aldehyde. And yes, this one is carbonyl this time. I definitely see the confusion because they look like they're in the same place for both charts. But yeah, this one is more like centered between 1500 and 2000. Does anyone know which molecule this one would be? G? Okay, why G and not A? Yeah. That's perfect. We don't have that aromatic peak around 1600, and then if you look at that 3000 region, there's no peaks on that side. So that definitely, good job, everyone. Um, okay, our third spectrum, which one is this? It's carboxylic acid. Perfect. Oh, actually, this one's a little bit tricky. Um, because we have two carboxylic acids. Um, in our options, and the graph is very there's a lot of peaks going on, but make your guess, and hopefully everyone's thinking the same thing. Yeah, yeah. Both of you are correct. This one is E. There's not a lot of or there's no alkene peaks at around 1600. Yeah. And this is a little bit hard to tell for sure because you don't really have information to be able to say with certainty. But all of you have a very good eye for the IR spectra to be able to come to the consensus that it is E. Very good job. And then our last spectra. What does this one look like? Or is there anything that we can easily read from this IR? Okay, Viona Y ester and Brandon Y nitrile. No worries, no worries. Um, and that's okay. You should have an IR chart when you do your exam. Um, Okay, do we have an idea of what molecule this one might be? Yeah, that's perfect. Um, Hold on, where's my pencil? Okay, yes, this one is J. And there's a few, well, um, true alkyne peak. Yes, so around 2200 you have your alkyne peak. So hold on, let me move up. If we look at our options, we have we have two alkynes, we have F and I, and then we have a nitrile peak. Um, Between Fi and J, which one is going to have the strongest peak and which one is going to have the weakest peak? Yeah, that's also true, Vienna. That helps. J strongest, F weakest. Yes, that's also correct. So if it was F, you wouldn't it's exactly symmetrical. You probably wouldn't even see a peak at all. With I, you would see a peak, but very weak. So this one, the dipoles kind of cancel each other out. This one might have a faint dipole, and then N will have a stronger dipole. Why is she stronger than I, even though aromatic isn't shown? Um, that aromatic, why is she stronger than I? That nitrile, aromatic doesn't really help with pull. I mean, if anything, it might kind of pull it in slightly opposite. Um, It I don't think the benzene ring would have much of an effect on it, just because that region is not for aromatic. Um, yeah, actually, let me quickly erase this. Kind of okay, yeah. That peak at J is just for the things that are connected to that triple bond. So when it's connected to a carbon and a nitrogen, it's stronger than just two carbons. Does that make sense to everyone? Perfect. Okay. Um, let's take a look. Let's see. How do you guys feel about, actually no, let's do it anyways. Um, okay, let's start from the bottom of this page and we'll work our way up. So I want us to start with problem C actually. Um, and so we have the IR, the CNMR, and the HNMR. And I want to see what clues you get from all three. So the first one is, so for part C, if we start with IR, what functional groups do we see in IR? Okay, I like it. Primary amine. Okay, so that makes sense because we have C3H9N. So you could definitely have two hydrogens with that nitrogen. With the CNMR, do we see any symmetry that's possible in this molecule? Yeah, okay. So we have two unique carbons. So that means that two carbons have to be identical to each other also. Um, And then we have HNMR. Okay, so HNMR has certain common patterns that help to that it helps to be familiar with. Does anyone see any of the common patterns that was talked about in the presentation on this HNMR? Isopropyl, fantastic. Okay, so let's say we have an isopropyl group. So this is our 6 hydrogen doublet. Um, these are the same thing. Oh, I should have done that. Hold on. Let me change my color. Okay. Oopsie daisies. Okay. And then we have our one hydrogen septet here. Um, and then we have a two hydrogen singlet. And also we need to put our amine somewhere. So where do you think that should go? Do I just add it on? Um, that last carbon that's sticking out? Far right, far left, either one. They're all symmetrical. So um, you could pick any. I can add it into the middle carbon too, but then we would kind of disrupt our isopropyl group. Um, I'm gonna write it onto the far right one here just because I've already marked the other carbon for the 6H doublet. But do you see that two hydrogen singlet peak? Do you see how that matches? And then you also have that symmetry with the two carbons on the end. Okay, good job. Um, hopefully when you take them one at a time, it's not as overwhelming. Okay, working backwards, let's go to B now. Are there any functional groups that you see in the IR? OH, perfect. Is there anything else? And if it doesn't look like there's anything else, that's okay too. I don't think so. Okay, solid. Um, so this molecule, based on the formula, we have 3 carbons, 8 hydrogens, and 2 oxygens. Oh, one thing I wanted to quickly go over. Is everyone familiar with the degrees of unsaturation? Okay, so is this molecule, let me quickly write it just in case. You should have twice plus 2, basically, as many hydrogens as you have carbons. And oxygen doesn't affect this. So if you have 3 carbons, you should have 8 hydrogens. So for this molecule, we can say it's fully saturated. And IR kind of confirms that anyways. So we won't have any double bonds, rings, anything like that. Another thing from this formula is that we have 2 oxygens. So keep that in mind. Okay, let's head over to our HNMR. And this shouldn't be a very, there's only 3 carbons in this molecule. So, and an alcohol and an oxygen somewhere. So hopefully that helps. Also, you all have control over this board as well. So if anyone would like to draw the molecule, if that's easier, you are more than welcome to. Oh, one last thing to note, there's no CNMR chart for this, but there is a CNMR listed below. Do you think there's any symmetry in this molecule? No symmetry. Okay, perfect. Does anyone want to draw it or try drawing something, or would you feel more comfortable breaking it down? We can talk through it if you would prefer. Okay, let's look at it that way then. So alcohol. How many hydrogens are in the alcohol? One hydrogen. So that will be this peak, right? Um, so we have an OH somewhere. And then we have to see what it's connected to. We also have a 3 hydrogen singlet. What does a 3 hydrogen usually look like? What is that? CH3? Okay, perfect. And it's a singlet. What does it mean that it's a singlet? No adjacent H. Okay. So how do you think that's possible? How would this methyl group just be? Okay, perfect. So let me put something like this over here. Okay, so this is our CH3, and it's next to an oxygen. And we know that there is an OH somewhere. And then we have 2H triplet. So 2H triplet means it itself is a CH2, and a triplet means it's next to what? Not CH3, but I can see why you would think that. Yes, perfect. So this is a CH2 next to a CH2. Um, this is a CH2 next to a CH2, and then this is also a CH2 next to a CH2. So how do you think that you can connect this oxygen and this alcohol? Yes, that's perfect. That is correct. Good job. Um, okay, let's see. Um, do you, hold on, let's see, what do we have left? Um, okay, so we have one question that is basically counting a molecule and seeing how many peaks there are for HNMR, NMR, and what that splitting would look like. Would you rather do that counting question, or would you rather do part A of this one where you're predicting the structure using this IR and CNMR? Okay. Is everyone else good with doing A? Okay. A being like 7A, right? Okay, perfect. Okay, so let's look at this IR. Do we see any noticeable functional groups in this IR? Um, and actually, sometimes I'm gonna be honest, IR is not the funnest to read, but or not the funnest to read, but like depending on the quality of the IR chart, certain things can be not as clear or clear. Then, anyways, okay, yes, what functional groups do we see here? 1620-ish. Okay, so hold on. This is 1600. This is 1700. This is 8. Hold on. 17, 16. Okay, aromatic. If we take a look at what's it called? Our formula, an aromatic would need how many degrees of unsaturation? Does it look like we have those 4 degrees of unsaturation? Okay. Yeah, this is 1 degree of unsaturation. So 1 degree of unsaturation can be any kind of double bond or a ring. So based on this not aromatic peak, which good job everyone, between 17 and 16, it's definitely sometimes confusing to tell, which is why I wanted to make that disclaimer about the chart. But hopefully when you have other clues, putting them together will help kind of be a detective and figure out what's going on. With 1 degree of unsaturation, what do we think this peak is? Carbonyl, that's a really good guess. Yeah, it matches up pretty, oh, sorry, hold on. Let me, do you know why do you think it's a carbonyl? Sorry, that line's a little bit tilted. Yeah, it's pretty close to 1700. Honestly, it's between 17 and 16, so it could really be anything. But yes, given that it's not possible for it to be aromatic, the next best guess that we have is carbonyl. Um, do we see anything above 3000 that's notable given the formula? Yes, good job, Brandon. Um, I like that. Okay, so this definitely carbonyl. Okay, anything above 3000 on the IR spectra. Um, okay, why could it be another NH2? Oh, secondary amine. Okay, do you guys think it's primary or secondary? If there is an amine. How many amine peaks do we see? Probably primary. Okay. Yes, that's good. Yes. Um, so because of both of these peaks here, I'm going to go ahead and we can deduce that this is a primary amine. Okay, so we have some kind of carbonyl in this molecule, and we have some kind of amine in this molecule. Do we see anything else below 3000 that could be interesting to us? Okay. Um, hold on, let me. Oh, another thing. So we have 5 carbons. Based on CNMR, do we see any symmetry? How many unique carbons do we have? 3 unique ones. Okay. So either we have some symmetry, or we have, yes. I mean, we definitely have to have symmetry. Um, but it can be, it doesn't have to be symmetry in the molecule, if that makes sense. It can be symmetry in groups. So for example, if you have like something, chlorine, bromine, I don't know, fluorine, you definitely don't have symmetry in the molecule, but if you had these 2 methyl groups sticking out of that, those would count, like you would only see 1 peak on CNMR for that, because these are identical methyl groups. So just something to keep in mind with CNMR, it doesn't necessarily have to be like very obvious symmetry in the molecule, like with a benzene ring or just a ring in general. Um, So, okay. Do we have any? Oh, okay. So primary amine, that's one thing we know. So primary amine has to be at the end of the molecule, right? So we have primary amine connected to something, and we have some kind of carbonyl in the middle. Or not in the middle necessarily, but somewhere in the molecule. Um, and if there's symmetry, does anyone have any idea of what we could have here? Like I was saying, if you have NH2 on one end, it's very likely your entire, I mean, it's not very likely that your entire molecule will be symmetrical, but you can have symmetry of certain carbon groups. T-butyl, okay. Do you think that's something that you want to connect to the amine? Do you want to try that, or do you want to have the T-butyl on another end? The other end? Okay. Okay, and then we put the ketone in the middle? Okay. Let me do NH2. Okay, so we have here, oh, hold on. That's not a ketone then. That's an 1, 2, 3, 4, 5, 6. Yeah, too many carbons. Okay, that's okay. That's okay. Don't worry about it. I think the best way to do um, like to put a structure together, especially when you don't really have very clear clues, is just keep guessing. You can guess and you can be like, that doesn't have enough carbons. Let me try and switch it like this and take away a carbon this way. And you're very likely to stumble upon something right. If you kind of feel like you're stumped at it and you've been looking at it for 5 minutes and nothing's happening, doesn't hurt to draw something. Hold on, let me get my pen working and we can try drawing an alternate thing. Okay, perfect. So let's do NH2. Let's try connecting the T-butyl to this. How do y'all feel about this? Still too many carbons. Okay. Um, hmm. Okay, what's a way that we can cut out one of the carbons here easily?
Sorry.
No, you're good. So make something like this. Oh no, hold on. Why are we thinking it's a T-butyl? That's a great question. We don't know, but it's a good way to get symmetry in the molecule. So it's not a bad suggestion. So like for that first one that we drew over here, we had 1, 2, 3 different carbons. Hold on. No, we had an extra carbon there anyways. But if you didn't have a T-butyl, it would be difficult to achieve that level of symmetry. And I'm gonna go ahead and give you guys a hint for this one. And how about cut the carbon in the middle? Oh, okay. So like this. So that gives us 1, 2, 3, 4, 5, and 1, 2, 3. Yeah, that looks very good. Good job, everyone. So we just kind of had to play around with it a little bit, but you have your 3 different carbons, and you have your carbonyl, and you have your primary amine. Um, let's see. Um, it's getting close to 9, so I'm going to try and wrap up. On this page, we have a question where there's a molecule, and it asks how many peaks you might see in HNMR and CNMR. So basically, what symmetry would you have? What the splitting pattern is. Do you want to do that question before you go, or does anyone have any other questions that you'd like to quickly go over and set instead? Any last minute things? Let's do this one. Okay. And if anyone needs to leave, then you are more than welcome to. Okay, so for, I do think you probably won't see a question like this on your test, because it's usually easier to have you put together a molecule or do like a reaction thing, but this is a good way to just confirm your knowledge. How many different peaks are expected in an HNMR? So, this is not like a splitting pattern question. This is just like unique, yeah, places where you have hydrogens next to you. So are there any places that wouldn't, actually, you know what, let's start with CNMR, because CNMR is easier. How many different signals do you expect in a CNMR? So let me start with this. Okay. Do we feel like these two could be identical? Yeah. Okay. I can keep doing this. Okay. Okay, that's yellow, so it doesn't show up really well, but just hold on. I'll change it to orange. Okay, that's a CNMR. Perfect. Let me double check that. Okay, we're actually kind of running out of colors maybe. They're like a little bit different, but they kind of, okay, but these are all new colors. Like the lighter pasteller, more pastel ones are different. I just wanted to say that. Okay, how many do we have so far? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Yeah, that looks right. 1, 2, 3, 4, 5, 6, 7, 8. Sorry, not 10. Okay, it's getting a little bit late. The pastel colors. My bad. So we have 1, 2, 3, 4, 5, 6, 7, 8. How many carbons do we have left? 8, 9. 10 is very close, but those two are actually not symmetrical because one has a double bond and the other one doesn't. It's very close. And this would be 11. And then I didn't see the double. Yeah, don't worry about it. It's also not very easy to see. Since we've drawn on it too. Okay, so for 5A, I think it's honestly way easier to work back this way. Once you have 11, you just need to cross out places where like you wouldn't have hydrogens. So are there any places where there's no hydrogens? If anyone wants to describe them, or you can use the pen yourself, and maybe you could use like a black or a gray. I'm getting the count wrong. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. This should be like a different color. There you go. Okay, I'm gonna make that gray. Okay. Yeah, sorry, those two are not identical. Okay, any places where you can't have hydrogens? Carbonyl, okay. DG. Oh, yeah, we have letters. Oh my God, that helps so much. Okay. I don't know why I didn't see that at all. G, um, L, DGI. Oh, sorry. Um, oh, DGJ. Yep, that's perfect. M, hold on. Yeah. Okay, so hold on. So now we have to look at the ones next to them. So, oh, hold on. What am I trying to say? Okay, so, okay, this counting is too difficult at this time of the night. But basically, yeah, so you're going to have these spots where you won't have any neighboring hydrogens next to it, so there won't be any peak for that. So how many hydrogen peaks should we have? So basically, this O will not, this O will be, hold on. The O will have a peak, but it's a singlet. 1 second. But basically, it should be 11 minus 3? No, 11 minus 4. You're like the things you identified was right. It's just like the actual theory behind it is it's not the places we crossed off themselves, but the actually, yes, it is the places we crossed off themselves. They don't have any hydrogens. I'm sorry, guys. Okay, so we have 7 peaks in HNMR because those areas without hydrogens don't have peaks. That was perfect. Good job, everyone. Um, for C, we're just going to look at A, B, C, N, and O and predict what the splitting is. So, for example, we just talked about O. So what would the multiplicity of O be? So if O doesn't have any hydrogens next to it, what is O's multiplicity? 1. Perfect. Okay, hold on, let's go back to the beginning. The N has 2 signals that are not symmetrical. N has 2 signals that are not symmetrical. What does that mean? Because a double bond can't rotate. Yeah, on our carbon thing, N and O, are you saying N has 2 for part C? For part A, how many different peaks are expected in an HNMR? Um, so we did count N for A. We just basically D isn't possible, G isn't possible, J isn't possible, and M isn't possible. But N can still have HNMR signals. You would have 8 signals because of 2 hydrogens on N. Oh, yes. You're very right. Okay, you're very right. Okay, you're right. Thank you so much for letting us know. Yes, it will have 8 peaks because of those 2 different hydrogens on N. Going back to C, um, what will the splitting pattern for N look like then? Doublet. Okay, perfect. So we have 2, or yeah, okay. For C, actually, let's start from A. A is probably easiest. What's the multiplicity of A? Triplet. Okay, so 3. Um,
Wait, I have a question.
yes.
Sorry. For N, would it be, wouldn't, I know the double bonds are like that weird, like splitting pattern. Would it be like a quartet of a doublet? Or doublet of a, since there's
For
two
N?
different signals? Because wouldn't one of the hydrogens be split by O or no?
Oh, I see what you're saying. No, because N is not right next to O. So there's N, then M, then O.
Okay, okay, yeah.
Yeah.
I just wanted to double check because like that gets confusing. Okay, thank
No,
you.
no, you're good. Um, I forgot about the double bond rule to begin with. Also, I want to make a big correction and another apology. My bad for the splitting thing. Y'all were right. It's definitely n plus 1, not the multiplication thing. That's why in the beginning that 4, 3, 2, 5, 1, or 4, 3, 2, 1, 5, the way that you had the key is correct. So we shouldn't have switched that 4 and 3. So it's just saying we have more, like if you're comparing a quartet to like a triplet of doublet. So triplet of doublet is then 5. Not, yeah, my bad. Okay, so can we go back and see it because the way you did it seemed right. Um, okay, yeah, we can definitely go back. Let's just wrap up B and C for part C, and then we can go back. So for B, what's the splitting pattern? 5, perfect. Um, 6. But yeah, okay, perfect. Sorry. Okay, it just took me a second. For C, how many neighboring hydrogens does C have? That's the tertiary. Um, so doublet, 5. Yeah, that's perfect. Um, Again, if anyone has any questions, I'm going to do my best to answer them. And I'm going to head back to the first uh, slide. Sorry, hold on. So we can take a look at that. And then after that, I'm going to go ahead and call time. Um, okay, so for 1B, the ranking that I wanted to put here really quickly okay. So this will still be 5 because triplet of septet is 3 and 7, 10. This one is still 1 because singlet. This one is still 2 because quartet. Um, and then this one is 3 because quartet of triplet gives you 5. And then this one is 4 because septet gives you 7. Is everyone okay with that?
Question.
Yeah.
So for number 3 in the ranking, so for the second one, um, since it's a quartet of a triplet, is the multiplicity a sextet? Is it still n plus
Quartet.
1? So we're doing 3 plus So we're doing the 3 on the left side and the 2 on the right side, and then so that's our n plus 1. So is it a sextet? I know it's like a quartet of a triplet, but
Oh, yeah.
so is
I
it?
see the question.
Yeah.
Or like once we have quartet of triplet, even though those are individually n plus 1, do we do n plus 1 at the end? I don't think so. I would double check that one more time because I can't guarantee it right now. But quartet of triplet, so the quartet is already n plus 1 and that triplet is already n plus 1. So hold on. Quartet of triplet, sorry. That's not 5. That's not 5. My bad. Doublet of triplet is 5. Quartet of triplet is 7? Yeah. And then we have 2 7s. So if we added the hydrogens next to it and then did n plus 1, my bad, I did n plus 1 twice. So the hydrogens on the methyl group there's 3 hydrogens here, and then there's 2 hydrogens here. That's how we get it. So then 3 plus 2 plus 1 is 6. And then for triplet of septet, that's 2 plus 6 plus 1. So that should be 9. Okay, now the ranking makes sense. Okay, 4, 3, 2, 1, 5, and you have 7 peaks, 6 peaks, 4 peaks, 1 peak, and then 9 peaks. Yeah. I would just double check counting signals for things with splittings just to make sure. Yeah, as you said in the beginning. So I misled y'all for a little bit. I'm really sorry. It's you take the adjacent hydrogens and you add 1. And that's how you would get it. Is everyone okay with what we've covered so far? Yeah. Okay, perfect. If you have any other questions, feel free to ask, or if there's something that has more explanation, a professor might be a better person to ask. No problem. Good luck, everyone, with your exams, and thank you all for coming. Have a good rest of your week. Bye.
Thank you, Safa. And I wanted to say hi. We were talking about you in PLTL today. I miss you.